Is the screen visible to you?
Ma'am.
Yes, okay, ma'am. So we'll start with adversarial search. Actually, this adversarial search is also called as game playing. Okay, and this is also called as game playing. So these are the topics that will be covered in this adversarial search. We'll see the introduction and optimal decision, minimax procedure, and alpha beta pruning. So in game playing, we have two main algorithms, minimax and alpha beta pruning. And we have certain games where we have imperfect information and perfect information. That also we will see. So this is about the introduction of game playing. As we discussed earlier, we saw the structure of AI tree. So when you consider artificial intelligence tree, so it have different branches. This game playing is one of the most important subfield of AI. So it involves abstract and pure form of competition. So, so previously we have discussed many algorithms, but there is no concept of competition, right? We saw informed research and uninformed research. So we have different algorithms and there is no concept of competition. But when you have game, so obviously when you have game concept, there will be the possibility of competition and winning and losing the game. So this topic is specifically designed for this competitive environment. Competitive environment. Do you remember we have discussed the types of environments in the first module? Uh, have you can you able to recollect the concept strategic environment? What is strategic environment? It is a special type. It comes under which type?
Ma'am, your voice keeps breaking.
Strategic environment. Hello, can you hear me now? Hello.
Yes, ma'am. But your voice keeps
Yes. Okay.
breaking in between.
Oh, okay. Okay. Can you recollect what is the meaning of strategic environment? Strategic. Can you hear me?
Yes, ma'am.
Yes. What is the meaning of strategic environment? We have discussed types of environment in the first module.
An environment in which the outcome is fixed based on the state of the AI is faced with.
Yeah, I couldn't hear you properly. What it is?
The environment in which and the outcome is fixed based on the state that AI is faced with.
So it is a special type of which environment?
Deterministic, ma'am. It will be
Yeah,
deterministic if it is completely dependent on only one AI and not other agents.
yeah. If it is depending on if the decision is depending on the multi-agent concept, then we have a special type called strategic, right? So for that, I told you the example chess playing. So your move when you consider you as a intelligent agent, and your moves are depending on the other agent also. So if you have this kind of environment, then the special type of deterministic environment is called the strategic environment. So in this game playing, most of the games, the decision or the move of a particular player is depending on the competitor. That depends on the number of players in the game also. There are two player game and three player, four player. You can have n number of players also. That depending on the game which we assume. So basically, in this game playing concept, we consider two-player game. So this is the competition environment. Previous algorithms did not consider this competition. They simply find the path from the source node to goal node. That is the objective of any searching algorithm. Whether it is informed search or uninformed search, the initial state is given to you and the goal state is given to you. You can find the path from source to destination. Varies, the steps varies depending on the algorithms which we choose. So here in game playing also, you can represent the state and the action. So what is the state and what will be the next action that we can decide. The 8 coins problem we have already discussed in chess, but there is no two-player concept, right? In 8 coins. Yes or no?
Yes,
That
ma'am.
is not, yeah, that is not a game playing because that is actually a simple problem. You will be given with the chessboard n cross n, and n queens will be given to you. You need to place the queens accordingly. That's it. There is no player concept and there is no competition winning or losing. That's it. So here to implement this game playing, we require very little world knowledge also. And so see here, some points are given. So when you have a game playing concept, it can also be represented as a search tree. This is very important. Even game playing can also be represented as the search tree. So searching is the main concept of an intelligent agent. So agent always tries to find the search tree, whether it is a tree or a graph, it always finds the path or it searches the path from the initial to goal state. So here, depending on the game, we need to define the initial state of the game. So this is the search problem definition in game playing. Initial state of the game we should know, and operators defining legal moves. So even in chess also we have some legal moves. You can move the queens only in the row wise or column wise or diagonal. Like that, for every game we have certain rules. So that rules we can consider as legal moves. And successor function. So actually successor function gives you the what will be the next state. If you are in a current state and if you do certain action, what will be the next state? So that is called successor function. If I am in a state A, if I do the action X, then my next state will be B. So A comma X equal to B. That gives you the successor function for any search algorithm. And terminal test defining end of game state. So for every game, there will be a terminal condition or end of the game is defined by different parameters. So that should also be defined. And goal test. So any search problem in the previous algorithms also we have the same concept goal test. In every step we need to the algorithm has to check whether the goal state is reached or not. And in game you have pathcast, or in some game you have utility and some game you have payoff function also. For example, in some games when you perform a certain move, sometimes you will get negative scores also, right? Negative scores also. That depends on the game. So these are the parameters we should understand clearly before converting your game problem into search tree. Actually, when you have a search problem, that can also be represented as search tree. And this is the characteristics of game playing. So always, so in game playing concept, always there is an unpredictable opponent. Yes or no? Can you able to predict the action of your opponent? That's not possible in many cases because there are n number of options. They may choose anything, so you cannot exactly predict the action of your opponent. So there is an uncertainty. There is an uncertainty in game playing because you also want to win and he or she also wants to win. So both of you are willing to win the game, So obviously there will be unpredictable actions by you or by your other opponent. So here the solution is a strategy. Solution for each problem is a strategy. See the third point, that is very important. Even if it is a deterministic environment, but when you have more than one agent, then that environment is called strategic environment, because the specific move or your action is depending on the opponent response or reply. Can you follow this?
Yes, ma'am.
Yes. Okay. And so the main concept here is unpredictable opponent. That's the main concept here, because you cannot predict the steps or moves of your opponent. And time limit. In some games, you have time limit also. So games are often played under strict time constraints and therefore must be very effectively handled. If there is no time constraint, you can have different steps. But if you have time limit or time constraint for a specific problem in the game playing concept, then within these many steps you need to win. So you have certain constraints also. So there will be time limited games. There is no restriction on times also in certain games. And see the second point. This is a special case. There are special games where the two players have exactly opposite goals. Exactly opposite goals. In some games, the goal of both the players are equal or same. The goal is same for both. But in some games, there will be opposite goals for every player. So these are the different types or characteristics of game playing. So game playing concept can be represented as the search problem, and it can be represented as a search tree also. And in general, this game's entire gaming concept can be divided into two perfect information games and imperfect information game. So that you can see in the last two lines. So if both players have the access to the same information, so they are given with same information, then that is perfect information game. But different information can be accessed by different player, then that is imperfect information games. So these are the things we need to consider when we solve the game playing problem. Okay, shall I move to the next one?
Yes, ma'am.
And so here in game playing concept, always we consider two players. The names of the players are Max and Min. Okay. So this is the universally accepted names for the players in artificial intelligence. Okay. Min and Max. Min and Max. So the aim of Max player is always he or she want to maximize his score, maximize the value, maybe score or value, because the concept is represented as a tree. So it always chooses the maximum value. And the other opponent name is minimum. So shortly we call it as min. So min always try to find the minimum value. So this is the condition. First condition is there are two players. Their names are Max and Min. And always the first move is performed by Max player. Keep in mind, always the first move is performed by Max player. Then the next turn is given to Min. Again, Max will do, then Min. So alternatively, they will do their action, but initial move is done by Max player. Can you follow?
Yes, ma'am.
Okay. And here, for in any game, depending on the nature of the game, a loser need to pay penalties and game points, right? So mostly we will do like that. A loser need to pay penalty and game points, or the credits are given to winning player. This is the concept in most of the game. So here the game is defined as a search problem, and it should have these components, important components, the initial state. For example, if you consider the chess, the initial or starting position on the board, which leads to further move. So that is the initial state, and the successor function I told you already. If you do certain action or a move from a particular state, then it will give you another state. So if you are in a current state, if you do certain action, that will result you in the next state or a new state. So that is called successor function. And terminal test is actually, this terminal test is uh, the final state which declares that the game is over or it is ended or terminal states. So these three are the important parameters. In the previous slide, we have discussed the definition of game playing. Actually, more or less they are same only. You need to understand the initial state of the game and the successor function and the terminal test. So these three parameters are very important for game playing. There are only two players. Their names are max and min. First move is always given to max. Okay. So here the search tree for the game concept is, call it as game tree. So in other algorithm we say that is search tree. Here we call it as game tree. So game tree is a graphical representation of initial state and legal moves for each side. Because we have two players, for max player we need to identify what are all the legal moves. And the turn will be given to min player next. Initially, the first move is given to max. So you need to identify what are the possible states for max. And in the next step, we need to identify what are all the legal moves possible for min based on the max action. Because after the first step, max has done some move, right? So depending on that, min has to follow this. So we will consider the game with X and O. What is the name of the game? Can you see the slide?
Tic-tac-toe.
Yes, tic-tac-toe. So X and O, these are the symbols we use normally. And this X symbol is given to max player and min player has the symbol O. Okay. So initially, see the root node. So that gives you the initial state. So the initial state is given to max, and he has to decide his first move. So how many options max have from the initial state? Because max has to place X somewhere in the board. So there are 9 locations because it is 3 cross 3. There are 9 options for X. Yes. Can you understand? Initially, the board is empty, right? Can you follow?
Yes, ma'am.
So initially, the board is empty. It is 3 cross 3. What is the objective of max player? He or she has to place X in any one of these places. So obviously, how many options he has? 9, right? See the second line. From the root node, you have 9 different options. X can be placed anywhere. Can you follow? Can you understand?
Ma'am, your voice is breaking.
And the so when you see the line, when you have the X placed in 9 different position, that option is given to min player. O is written near the second line. The second row. In this case, into max player has 9 different option to place X. He can place X anywhere. There are 9 different options. So, hello, hello. Can you hear me? Hello.
Ma'am, your
Yes, ma'am.
voice
Now
keeps
it's clear.
now we can hear you, but your voice keeps breaking in between, ma'am.
Hello. Okay, I'll check my network. Can you hear me now?
Yes, ma'am.
Hello. Hello. Can you hear me now?
Yes, ma'am. Yes,
Yes,
ma'am.
ma'am.
Okay. So can you follow this diagram? The initial state is empty. So Max player has the first action. So he's able to do his first move. So how many options he has? 9 options, right? Can you follow?
Yes, ma'am.
Okay. First, hello. Hello, can you hear me?
Yes, ma'am.
Yes, okay. And second move should be done by min player. So min player can see all these options, but in actual game, there may be only one option min player has. So by seeing that, how many options this min player has to place his woe? Initially, max player has empty board, so he has 9 different options to place his X. But in the real game, he has to choose any one of these, right? Then, by seeing that, how many options min player has? So totally, how many empty cells now?
8.
8. So min player has 8 different options. So when you convert your tic-tac-toe problem into this game tree, initially max player has the empty board, then he has 9 different options to place his X. Fun for every option, for every option. So that's why see the third line, max of X. So for every option, this min player can place his bow in 8 different positions because already one cell is occupied by X. So he has 8 different options. So for that option, for any of these option, again, the max player has 7 different options. So like this game tree will grow like anything. Just imagine this is a 3x3 structure. So when you represent the game playing concept in a tree structure, actually it is a complicated one also, but yes, for some problem, it is easy to represent the problem in a game tree structure, and we can find the values also. What will be the best move or best score from the initial state to goal state that we can easily identify. So keep this diagram in your mind, and I'll tell you. So here, game tree is a graphical representation of initial state and legal moves for each side. Can you understand? Because in that tree, you have an initial state that is empty board and the legal moves for every opponent. For max and min, all possible moves are given in the game tree. So it is for this game, specific game. So for any game, you can represent the concept like this. So initially, max has 9 possible move from initial state, and max is given with the symbol X and min is given with O symbol, and the leaf nodes are entitled by utility value. So the max is assumed with high values because always max tries to maximize his score, and min is with low value. So the best move is always determined by max by using the search tree. So always we consider max will do the first move, and when you find the whenever you want to win the game, we always concentrate on the max player. These are the common rule for any game playing. So this is one example. So for this, the initial state and all possible legal moves are given for both the players, both min and max. And this is a strategic one. The reason is the sequence of moves which achieves win state or terminal state or goal state is actually a search problem, because actually every game is played in a strategic environment. The reason is the action of a particular agent is depending on the on his opponent also. So this is not, even though it is in a deterministic environment, but that is a slight variation. There are multi-agent uh, depending on the game. So it is a strategic environment. And so this is one example. I will give you another. So see here, we will see this minimax tree first, then we will go to algorithm, then you can easily understand. So how many levels are there in this tree? See, you can see the root symbol with upward triangle, right?
Yes, ma'am.
So upward triangle. So that initial move is given to max player. And the next level you can see downward triangle, because max always wants to maximize, that's why upward triangle is given, and min player always wants to minimize his score, so downward triangle is given for min player. And this is actually a two play game because we have only two levels, and see the last level, the leaf nodes. Normally in game playing, only the leaf node consists of certain value. From that, we need to identify the value for intermediate node and the root node. This is the concept in game playing. Always you will be given with the utility value for leaf nodes. Can you understand? You will be given with this kind of tree structure, but no value will be given for intermediate nodes and the root node. Only the last one, the leaf node, 3, 12, 8, 2, 4, 6, 14, 5, and 2 will be given to you. This is the concept. Only leaf node values are given to you. So we need to identify the values of intermediate nodes. So in the first level, we need to start with the max. And next level, it is for min, right? Because alternatively they have to move, they have to do actions, they have to take their move alternatively. Initially we need to start with max, so the root node option is given to max, and the next level is given to min. And in the third level we have leaf nodes. It consists of utility value. So consider the first branch alone, the first three values, because these three leaf nodes are from the same root node. You have 3, 12, and 8, right? Can you understand?
Yes, ma'am.
Okay. In 3, 12, and 8, what is the minimum value? Because that intermediate root node is for min player. What is the minimum value among these three? 3, 12, and 8? It is 3. Okay. So the value 3 is written for the particular node. Can you understand why we got 3 here?
Yes, ma'am.
And see the second structure. You have three nodes, successor nodes, 2, 4, and 6. Out of this, which one is small?
2.
So now you have intermediate values. Initially, the problem is given for you with the leaf nodes utility value alone. Prior to value of the previous 11 nodes. So we have the 3 layers, max, min, and leaf node. But in actual cases, you have max, min, again max, min, then again max, min, and leaf nodes. Then you need to start from the bottom line, the leaf nodes. So from the leaf nodes, you need to identify which player has the option, the previous one, whether it is a max or min. Accordingly, you have to choose the minimum or maximum value. So now you have the intermediate value 3, 2, and 2. And now you have to identify the root node value. So the root node is responsible for which player? Max player. So what is the maximum value among these three? 3, 2, 2. 3 is the maximum value. Okay. Can you understand?
Yes, ma'am.
Yes. So this is one example. So with this I stop because we need to see the algorithm and we have to relate this concept how the moves from the initial state to the utility value leads to winning. That we need to see. So with this I stop.